All right, so it is my very great pleasure to introduce Dr. Will Dawson, who is visiting us from Lawrence Livermore, one of the closer virtual visits we've had. He is a technical research scientist at LNLL and has been working for a long time in engineering, astronomy, and physics. Does various interesting national security things, and is also working on the LSST, the Hubble Space Telescope Reionization Lensing Cluster Survey, and is performing a survey of Milky Way black holes, which I think is what he's going to talk about today. So thank you very much again. Everyone, please feel free to interrupt Will with questions whenever you might have them. Yeah, thank you. Please take it away.
All right. Well, I want to thank you again, Simeon, for having me. Having present at your colloquium, I'm excited to do this. I'm really interested to engaging. And so again, please interrupt with questions as we go along.
Okay.
So today,
you've got your presenter view rather than your screen's flipped.
How about now? Is this any better?
Yes, perfect.
Okay, thank you. All right, so today I'm going to talk about finding perhaps too many black holes in the Milky Way. Now, traditionally, I've devoted most of my scientific career to the study of dark matter. And so then I think it's a natural question, why am I talking about black holes? Because I think, when people think about compact object, dark matter, or machos, they think about something like this. And so what I'm showing here is the compact object mass, and it's over, many orders of magnitude. And then on the y-axis here, we've got the dark matter fraction. So this is the amount of dark matter that's composed of a compact object at any one of these masses, assuming that it's all that mass. And the blue regions, are all of the constraints on this fraction of dark matter that machos could be. Some of the original work was done with Milky Way microlensing constraints, such as the Macho project at Lawrence Livermore National Lab back in the 90s, OGLE and Eros, etc. And since then, people have really filled in this space with a number of constraints. And so there doesn't seem to be any room whatsoever for machos to make up an appreciable fraction or any significant fraction whatsoever of dark matter. And again, this is over many orders of magnitude. So I wouldn't be talking about this if it really weren't for one thing, and that was LIGO, right? So as everyone knows, LIGO started detecting these intermediate mass black holes, and they were detecting them at such a rate that it became curious. What's up with this? We thought that a lot of this had been ruled out, and so it really excited a lot of people to start considering whether or not black holes could be dark matter. And so George Chapline, who's a physicist at the lab, he's been here for decades. He came up to us one day, us astronomers, and he was like, is there any way that you can probe whether or not these intermediate mass black holes are making up dark matter? And I said, why would we bother doing that? Referring to the previous plot. And he's like, well, I wrote this paper in 1971, and I really think that there's some strong theoretical arguments for primordial black holes being what LIGO is seeing right now. And if they're primordial black holes, then they could make up all of dark matter. And so I started exploring it a little bit more, and also motivated by a number of other works. I gave this more consideration than I initially was inclined to. And there were works by Simeon, for example, that were seminal to this in 2016, asking the question, did LIGO detect dark matter, and investigating the event rate at which LIGO was finding black holes at the time. And it seemed to suggest that it is conceivable. And then there were other theoretical works, such as George Chapline's work on the mass spectrum. There was evidence at the time of some intermediate mass black holes being found and nearby dwarf galaxies. in clusters. And then also there were other microlensing results coming out at the time, finding, 10 solar mass black holes. And so given all of this, I thought that it was worth a closer look. And so I started to dig into these constraints that I was showing earlier. And so, for example, just zooming in on one mass range, in particular the intermediate mass black hole mass range, these were the Macho constraints circa 2008. So, there was a very small window here, but it couldn't, that's not enough to make up all of dark matter. And it was largely ruled out. You had constraints from microlensing probes. You had constraints from the cosmic microwave background, and also, wide binary constraints. And I won't go into too much detail given our limited time today, but whenever I started looking into these papers, it was clear that there were, some pretty strong assumptions made in particular the wide binary and CMB restraints, and not only complex assumptions, but there was also complex astrophysics involved. So you had several degrees of separation between the observations and then the actual constraints. And so looking into some of these, as other works by other groups such as Ali Hamoud and Kamikowski in 2016, they investigated the CMB results, I think also motivated by the LIGO discoveries, like what's going on here, are these constraints as tight as they claim to be? And so whenever they started investigating some of the systematics and assumptions that were made in these constraints, they found that, these constraints were not nearly as tight as originally claimed. And in fact, Ostreicher, who was part of the original CMB constraints, said that the limits that Riccati and I reached for black hole numbers were far too severe. And then around the same time, a little bit previous, you had other people investigating these wide binary constraints and reaching similar conclusions. But the story is complex and evolving. One other important thing that came out of the Ali Hamoud and Kamikowski work was some estimate of the uncertainty in these constraints, whereas before it was just, these are the constraints. And they acknowledged the fact that given the assumptions that were going in, there was really, even with their updated constraint, there was an order of magnitude uncertainty in where that lied. In the meantime, you had other constraints coming online, such as Brandt's work with dwarf galaxies, saying that if you had a large population of these intermediate mass black holes, they would sink to the center of these dwarfs, absorbing, transferring their energy through dynamic friction to the stars, and the stars would actually puff up. And since we don't see that, they said we can claim that you couldn't possibly have this many black holes. But again, you look at this constraint, and it also has complex assumptions and astrophysics involved in it. And so, for example, they originally assumed that there was no central massive black hole, and but there's been evidence of there being massive black holes at the center of these dwarfs by a number of authors. They also assumed a delta function in the intermediate mass halo mass function, and why that's important is they were assuming that you had these intermediate mass black holes of a few hundred solar masses, and through dynamic friction they were sinking to the center, and all of their energy was going into the stars, puffing it out. But if you have a continuous mass function, as most theorists would agree that you have to have if you're dealing with primordial black holes, then you also could have a large population of black holes that are of lower mass too. So you've got lower mass and higher mass, and so the higher mass ones are sinking to the center of these galaxies, and then those lower mass black holes would be absorbing some of that energy as well. So you wouldn't get nearly as much energetic puffing up of these stars. And I won't go into everything else here, but the idea is that we're seeing this trend that people in these constraints, whenever they're making them, they're initially, making some, although they might seem like reasonable assumptions, they're actually quite strong assumptions, and they're not fully investigating the uncertainty of what happens if you relax those assumptions. Fortunately, the field has been improving though, and you know, the gray region here, these are, if you look at what are the most strict constraints from previous years, and then the blue ones are the updated constraints as people have started to investigate these systematics and look at this uncertainty. You can see that in many cases you have, you know, orders of magnitude shifts in these constraints. And this, even now, the story isn't complete because a lot of these assumptions, you know, a lot of these probes still rely on several degrees of separation between the observations and the actual dark matter constraint. And you know, this is really interesting. This is a phenomenon that I saw a lot with the emerging galaxy clusters and self-interacting dark matter field as well. And so, you know, I think it's a trend. I haven't heard a lot of people talking about it specifically, but you know, it's a form of bias, and you know, I've termed it null bias. And I think it's actually an extension of pathological science. And so for anyone not familiar with it, I think every graduate student
What?
Are you going to tune in for the
would be,
Yeah, I'm listening to it right now.
I think every graduate student, sorry, okay, I think every graduate student and every scientist would really benefit from going back and looking at Irvin Langmuir's 1953 talk on pathological science. And there's a great write-up of this in Physics Today, October 1989. And this is one of the most important lessons taught to me by Tony Tyson. And so I think null bias is a form of this. And basically, you know, what it relates to is scientists aren't necessarily as rigorous with null detections as they are with positive detections. You know, you get a positive detection if it's something exciting. The first thing you do is you think of all the ways that it could be wrong, and you try to, you know, prove yourself wrong. I don't see the same rigor in general with null detections. That's not true of all fields. Some are very rigorous, but you see this a lot in astronomy, for example. And I think the areas where you see this show up a lot is whenever you're dealing with fringe science. You know, for example, black hole dark matter. That's definitely a fringe science topic, I think. And so then it, you know, it's a lot more comfortable to rule things out. You don't necessarily feel the need that you're ruling something, you know, all that significant out. Also, you see this with small sample size. You oftentimes see that the uncertainty characterization or the propagation is rarely done, you know, correctly or thoroughly with the same rigor that you get with positive signals. And then there's qualitative rather than quantitative support of many of the assumptions. And it's also, whenever it's complex, again, whenever you have several degrees of separation between observation and constraint, it's also more likely that null bias is going to creep in. And the other interesting thing that can happen too is, I think I've seen this where if you have multiple existing null experiments and you've got a new null experiment building on top of this, there's two psychological phenomena going on here. One, there's a natural tendency to take the existing null constraints at face value. And so if you're ruling out something that's already been ruled out, you know, you can feel pretty comfortable about that. You might not approach it with the same rigor. Now, this isn't to say that if you see any one of these types of trends present that null bias is there. But I think as you start to check off more and more of these signatures of null bias, you should be more wary of it. And I think that you're seeing a lot of this in the compact object constraints. And so, like I said, the field is getting better. People are starting to explore assumptions that were initially made, and you're seeing shifts. And I think the precision of these constraints are getting better with time. And so whenever we were approaching this problem, I said, okay, well, let's try to make as direct a measurement as we possibly can. All right, and the best way that we could think how to do this was by extending the existing macho and compact object, the microlensing constraints, because as far as I'm concerned, I think that this is as close as you can get to a direct probe of compact objects or intermediate mass black hole dark matter as you can. And so the idea was to use the same same techniques that were used in the 90s with these microlensing experiments and extend the results into higher mass regime. And so that's what we set out to do. And so let me talk a little bit about gravitational microlensing and how we're using that, one, to find black holes, but also to constrain their abundance. And so gravitational microlensing is just another form of gravitational lensing, which was first posited by Einstein, and actually even before that. But what happens here is you've got some observers on Earth. There's some source star, some background star emitting light. And then as that light travels outward, if some of it passes by a massive object called a lens here, which is gravitationally distorting space-time, then those curvatures of space-time can actually change the path of the light. And what you can get is you can get a focusing of that light onto the observer. And so, for example, here you've got two rays. And then, so what the observer will see is they'll actually see two images of that star. So they'll see what's shown here in blue is they'll see what's called a plus and a minus image. And if you project this on the sky, then it looks something like this, where you've, if this is centered on the lens, you have the source, which you're no longer seeing, but instead of seeing the source, you're actually seeing a lensed image. You're seeing just outside of the Einstein radius, and then one on the inside. And so, and in principle, you know, gravitational microlensing is no different than strong lensing, some of these beautiful images that Hubble sees. But the real difference with microlensing versus, you know, all of those beautiful images that you see from Hubble of strong lenses is the resolution scale here. And so, for example, you know, the relative ground-based resolution is much, much larger than, or the point spread function, how much this light gets spread out is much larger than the separation of these two images. And so you don't actually see these multiple images, but instead, what's important here is that you see a brightening of the source, because you've gotten extra light from this gravitational lensing. And so you see, it's as though the source got brighter. Now, that would be nearly impossible to detect in its own right, because you couldn't tell if you were just looking at an intrinsically bright star or one that had been lensed. And the only reason that this is really detectable is because this is a transient phenomena here. And so this is a simulation by Scott Gowdy. But what we're seeing here is the perspective of the observer looking at the lens. And then what happens is all of this stuff is moving as stars move throughout the Milky Way. And so in this reference frame, the background star shown as this red circle, you know, it happens to move through the Einstein radius of this source. And what you'll see is you see these multiple images going past in time. And the other thing that's shown in the bottom panel, which is the really important one for gravitational microlensing, is you see a magnification of this source. And so this background star, before it's lensed, it's got a certain brightness. And then as it passes through the Einstein radius of this lens, more and more light is magnified. And so it appears brighter with time. And so that's the transient signal that we're looking for whenever we're conducting one of these astronomical surveys. Another really important thing with gravitational lensing, and a tool that we'll use, is when the duration of this event, so when this time scale of this microlensing event lasts longer than a year, you get another effect, which is very important. And so what happens in that case, as Earth is going around, the geometry is changing. And so instead of this smooth, symmetric rise and fall of your magnification, you'll get parallactic wiggles, or what are called parallactic wiggles, as this geometry changes. And you can see that the period of these, they naturally have a 1-year period. And so this is a really interesting signature that we're going to use in this analysis. And this has been used to identify recently, black holes. So for example, from this research, this was done with the OGLE astronomical survey, but this is real data taken from that survey. And so you can see the lensing event, but you can also see that whenever you subtract off what's called the heliocentric or that symmetric lensing event, you get these parallactic wiggles, and they have this characteristic 1 year time frame. And so here's a approximately 9 solar mass black hole that was detected, and 1 solar mass neutron star. Now, microlensing is not perfect. And so even with that additional constraint, so I forgot to mention, but this parallax, the amplitude of this parallax is a function of 1 over the mass. And so this provides an additional constraint on the mass of the lens, which is nice, especially whenever you're trying to determine if what was doing the lensing was a black hole or if it's some small star. But even so, you have this degeneracy. It's called the mass distance degeneracy. And the way to think about this, intuitively, is it's a lot like a magnifying glass. And so, if you can think about this, if you think about optics 101 in physics, right? The magnification is largest whenever the lens is halfway between the observer and the thing that you're looking at. If you move that magnifying glass and you set it right on top of the piece of paper that you're looking at, you'll get no magnification. Conversely, if you bring the magnifying glass right up to your eye, you'll also get no magnification. And so there's this difficulty in telling whether or not you're getting a large amount of magnification just because of the position of the lens, or if because it's a massive object. And so, for example, you could get the same amount of magnification if you've got a very massive object and it's sitting close by Earth. Or you could have the same amount of magnification if it's a lower mass object and it happens to be between you and the background star that's doing the lensing. And so we're left with this problem, right? If you can't tell how massive the lens is, how can you tell if it's a black hole? Especially if there's the possibility that the lens is a low mass star and you have blending issues, then you might not be able to see that it's a luminous object until it moves far away from the actual lens or the source. And so there's 2 approaches here. You could take an additional measurement like astrometric microlensing to try to break this degeneracy, or you could also just accept this uncertainty and use large numbers and a statistical approach to beat down this uncertainty. And so I'll talk through these 2 approaches here. And so what I was talking about previously is kind of called photometric paralensing. So you're looking at how the photometry of these stars changed with time due to the lensing. But what I'm going to talk about now is astrometric microlensing, and this is the impact that the lensing event has on the apparent position of the star that you're looking at. And so here's another movie. This one is the observer source frame, for example. And so the lens in this case is moving in this frame of reference. And now the important thing that you can see here is that whenever the lens passes by, what you get is you get that shift of those 2 lensed images, right? And now if you blend those together with your seeing kernel, so the light gets blended together, it gets mixed together as that light passes through the atmosphere or your optics, you only see the combination of those 2 lensed images. But because one image is brighter than the other, you get this apparent source location, which is shown as the solid red dot. And so in this particular example, you can see what's happening to the centroid of those lensed images on the sky. And so it's actually, you could observe what would happen is your background source would appear as though it's moving in this ellipse. And so if you can very precisely measure the location of that star, you can get an additional constraint on the mass. The nice thing about this about this as a complementary probe, in addition to the photometric microlensing, is that your peak magnification happens at this time, but your peak astrometric microlensing, so the largest signal, actually occurs at a later time. And so you can identify an event based off of its photometry, and then you'll have time to go and follow it up with a very precise astrometric measurement. And so how do you actually make this? Again, because the key thing here is you're talking about milli-arc seconds change in position, which is very small, given that the scale of resolution of something like a regular ground-based telescope that doesn't have adaptive optics, it's usually on the order of maybe half an arc second to an arc second. However, you're talking about needing milli-arc second precision here. And so one way that we're doing this, and this is in collaboration with Jessica Liu at UC Berkeley, is using Keck adaptive optics. And so the same techniques that are used to very accurately map the movement of stars in the center of the Milky Way, which this year won the Nobel Prize, that same technique can be used to look at a field of stars and see this astrometric signal. And so Jessica Liu has done this. And in this case, if the star weren't being lensed, you'd expect it to trace out this this dash trajectory. But what we see in this particular event, this is a lensing event, you can see that the trajectory of the star actually follows what would be expected if this source were being lensed. And so then you can use that information to in its own right, just with astrometric microlensing, estimate the mass of the lens, which is what Jessica did here. The really powerful thing comes into play whenever you combine these measurements. And so here we're looking at where the lens is and what the lens mass is. And so you can see the traditional, lens mass degeneracy. You can't really constrain it from photometry alone. But whenever you combine that with the astrometry here in the blue, you can combine those constraints and get a very accurate mass estimate. All right, but everything isn't as rosy as it sounds here, because there are a number of challenges that come along with astrometric microlensing. And so first of all, that parallax signal, this deviation of the trajectory of the star relative to a linear trajectory, that decreases with mass. And so we're talking about looking at intermediate mass black holes. And so the more massive they are, the less that deviation is. And so this requires very high precision astrometry. The other challenge is that this requires, ground-based adaptive optics or space-based imaging, which are both very expensive. And typically, because these have very limited fields of view, you can only follow up one event at a time. And so, or per field of view. And then, also, like we said, the larger the mass, the longer the event lasts. And so that's actually both a blessing and a curse, because one, it gives you more time, and so you can take more observations to beat down your statistical noise. But at the same time, you're using other stars as your reference frame, and those stars are moving with time. And so whenever you're looking at about 8,000 microlensing events coming out of one of these photometric surveys, this is just far too many events to follow up all with astrometric microlensing. And so I think this is very powerful, but we can't rely on it wholly. And so let's talk about more of a statistical approach to finding these black holes. And a lot of this work, that I'm going to talk about really comes back, and Casey Lam, who is a fantastic graduate student at UC Berkeley, I think she's one of the best graduate students I've ever worked with. She's done some really impressive theoretical and simulation work that has really enabled a new regime of statistical microlensing studies. And so what she's done here, she's developed a simulation code where it starts off with a stellar model of the Milky Way. You can look at a component. So each component of the Milky Way is modeled. So the stars within the bulge of the Milky Way, they have very different characteristics than the stars within the disk. And those all impact your microlensing forecasts. They also have different motions. And so that's all been included in this analysis. And then it even takes into account the age of these stars and the different ages of the components. So the bulge of the Milky Way is a different age than the disk. She then puts all of that into stellar evolution theory code, and then she maps out the trajectory of these stars in this simulation, and then looks for when stars pass within the line of sight of one another and create microlensing events. And then additionally, you can add in your survey constraints. So some surveys, they can't see very faint stars, for example. And so that's all factored in. And then what's spit out is a distribution of microlensing events, or expected number of microlensing events, as well as their mass, their component, etc. And so you can do things now, like if you look at the distribution of the time scale of these microlensing events, and you look at the abundance of the microlensing events from the simulation, because she knows which objects are a stellar lens, which ones are white dwarfs or neutron stars, she can really start to break out that component. And so again, because more massive objects produce a larger Einstein radius, which leads to a longer timescale event, it's not surprising here that the black holes tend to produce microlensing events that have longer timescales. And so you can also, break this down and say, if I'm looking at a particular timescale, what's the probability of it being a black hole or a stellar type event? And so you can see if you're dealing with very short timescale events, it's almost certainly that you're dealing with a stellar lens. So just a regular, vanilla type star is producing this microlensing event. However, if you start to push out into these longer timescale events, so if you measure microlensing events with a longer timescale, you can see that it starts to get around the 50-50, chance of it being a black hole. And so we knew that this was the area that you wanted to focus on, but the powerful thing here is that we're now able to start to quantify this. You can also do
Can I ask a question?
Yes, please.
About the previous slide.
Sure.
These are assuming the black holes are stellar remnants, not the dark matter being black holes, right?
Yes, thank
Okay.
you. That's a very important point here. So this code currently, what I'm showing is just assuming regular stellar evolved black holes. And so this took stars, it plugged it into an initial final mass relation, predicted what the mass of those stars would be. And so this is just pure stellar evolved black holes, not primordial black holes. However, you can, with the simulation, you can start to ask the question, you can start to inject black holes into this. And you can say, okay, if I did have black hole dark matter, and if it were a given percentage, how would that change, for example, this expected distribution of the time scale of these microlensing events for a survey? And so that's what you're seeing here. And so the black curve is what I was showing earlier, no black hole dark matter. But then these other curves show you how this distribution changes as you ramp up the abundance of primordial black hole dark matter. And so this is why this tool is also very powerful. We've got this control. I think so that's powerful. But the most powerful thing that came out of Casey's work with us was really a completely new means of finding black holes. And so everything I talked about before, it really involved, combining that with astrometry. Maybe you had parallax, you would have a large amount of uncertainty in what the mass was. You might be able to do that. But whenever we look at the parameter space of the distribution of these different populations from the simulation, we see that if you look at the time scale of the microlensing event, so how long the microlensing event lasts, as well as the parallax, so this pi e, that's kind of the amplitude of those wiggles due to the parallactic motion as Earth is going around, and that's changing the geometry. You see that there's a big separation between the black holes, these massive objects, and the rest of the stellar objects here. And so even though you couldn't do better than doing like a 50% estimate with time only, once you look at this two-dimensional space, you can really start to separate the objects. And the reason why, the physics behind this is that the time scale of the microlensing event is theta e over mu rel. I know forgive the jargon here. The most important thing is that the time scale of the event scales with the square root of the mass, whereas the parallax here, the amplitude of those wiggles, goes down with 1 over the square root of the mass. Whereas everything else, the other important parameters here, drive the distribution in other dimensions. Mass is the only thing that really drives it down and to the right. And so if you can measure the time scale of the event, and you can measure the parallax of the event, then you can use those two constraints to determine whether or not this is a black hole. And so just another plug for astrometric microlensing. If you can do astrometric microlensing, you have an even this is kind of the amplitude of that astrometric shift. If you can measure both the parallax and the astrometry, you can even do an even better job of separating the black holes from the other lensing events. And so this is a really powerful technique. And so motivated by this, we wanted to apply this to real data to search for actual black holes. And so one of the best microlensing surveys to date is actually what's this OGLE survey. And there's been a few versions of it, 3 and 4. The important thing here is that this is focused on the bulge of the Milky Way. And so the very center of the Milky Way is actually right here. There's too much dust in the plane of the galaxy, which is why they don't detect any events there. They don't really survey that because that light all gets absorbed by the intervening dust. And so they focus just above and below the bulge. And the other important thing here is that they have about 3,500 microlensing events from their OGLE 3 survey and 8,000 events from their OGLE 4 survey. And this is public archival data. And so we started playing around with this, fitting the microlensing model to this, and in particular fitting the Einstein crossing time and the parallax, as well as the other components of the model, which we'll skip over in the broader interest. And so this is one particular example of one of our initial fits, where we were fitting just parallax, the parallax microlensing model, to this photometric light curve from OGLE. And this was an MCMC type of analysis, so a Bayesian type of analysis. And what we ended up with was a bunch of Markov chain Monte Carlo particles mapping out essentially the posterior probability of this event lying within this space. And you can see that we were pretty excited whenever we first saw this event, because even though the uncertainty was rather large, it was all lying within kind of this black hole region. And so then, we did a few more things to estimate the mass of this of this event and of this lens, and we found that it was about 10 solar masses with one method versus 6. So this importance sampling method is if you just importance sampled the particles from the simulation. And so for example, if it lined up with these type black holes and they were about 10 solar masses, you'd end up with something close to 10 solar masses. Whereas this Monte Carlo type approach, this was a more agnostic approach, where it wasn't dependent on the simulation, what went into that, but it just marginalized over other parameters. Now, quick spoiler, this is not a black hole lensing event. And so what I'm going to show here is some very rough results. So please forgive the quality of these plots, but it tells a story. And so this was another event that we found, after that previous one. Whenever we fit our model to this, and we estimated the time scale, it was 900 days. So this is way out here in this parameter space. And if you play the same mass estimation game, you end up with something like a 700 solar mass. And so we're like, okay, wow, that seems big. But I don't know if you can see something here. It's somewhat subtle, but the red is the data, and this black line is kind of the best fit, and it's just mapped where the data is, and so it doesn't show the model actually where there are gaps in the data. But the important thing here is look over on this side. You can see it does a fine job fitting this data, but over here something was up. It wasn't really fitting that. And so one of the things that we tried was we just added a linear component to this. So we had our microlensing model plus just a linear trend. And so we added that. So our model was slightly more complex. But whenever we did this, we found that the time scale of this lensing event went from 700 days down to 70 days. And so this is now not really an extreme event. And whenever we looked at the distribution of this linear trend, in the data, we found that it was actually pervasive. And so there was a broad distribution where in some cases, you had a very strong linear trend to that photometry. And so, without access to the raw data, we couldn't exactly tell what was causing that linear trend, but we could think of no physical argument to definitely fit no theoretical model for black hole lensing. And so it seems to be a calibration issue with the survey. But this is archival data. We don't have access to the raw pixel level data. We only have access to the light curves.
So
now on top of this,
how does it? I don't quite see how the fit works. That t goes from 700 to 70 when you add the linear trend. It isn't.
Yeah. So what this was doing was it was trying to broaden this out even more to compensate. So it was trying to make this wider to compensate for this this linear trend.
Oh, I see. So it's just trying to pull the last bit up. Basically, it's just trying to widen the fit. Okay, thanks.
That's right. And so it's just widening that. And so so this was surprising to us. Not to mention that on top of this, there are other systematics due to unmodeled intrinsic variability. Stars fluctuate, and that wasn't part of our model either, but that happens in reality. And so we started to get concerned about that as a potential bias as well. And so our solution was to combine a Gaussian process. And so this is a way of combining multiple component Gaussians to map out variability to fit random variable. This is very powerful technique. I don't have time to go into it here, but the idea here is that we took our microlensing parallax model, which was essentially our physics, and then used the Gaussian process to capture this variability as well as linear trend. And whenever we did this, we found that it did a pretty good job of doing that. And so here's an example of that fit, and we've published this work. But this panel in the middle, so the top shows the raw data, the panel in the middle shows the Gaussian process fit, and then this panel shows you what's left of the microlensing fit after you take out the Gaussian process component, this model. And then the very bottom panel shows you the residual. So this is once you've detrended the data based off of both the Gaussian process and the parallax. And you can see that it does a pretty good job there. Here's another, you can ask the question though, but can't this Gaussian process that is modeling these wiggles in the data and these linear trends, couldn't that eat essentially your parallax signal? And so we were very concerned about that as well. Here's an example where you see a very strong parallax, a very strong Gaussian process, noisy component to the data. But whenever we took that out, we still saw we still picked up on the microlensing parallax. And so it didn't eat it all up. This is just an example case. And these are just case by case, just to look at the data. That's not satisfying. What we want is we want to look at, what happens on average here. And so one of the ways that we did this was we took actual real data to try to see if the Gaussian process was introducing a bias, or if we had bias from other types of events or other types of effects. And so we took microlensing events from the survey data that were on the shorter time scale, like this one. And then we masked out the data around the actual microlensing events. So we deleted that. And then we had data that had all of the, ugliness of the real data. And then we injected known microlensing events into this data, ran our fit on this, and then investigated the bias. And so what you'd expect here, ideally, is the mean of your bias would be near 0, and the variance would actually be close to 1. And so we see that there is some residual bias, although it's not that significant here. And so we felt comfortable that we weren't we were doing as good of a job as we could, and there wasn't a major source of bias. And so given that, we started looking, okay, well, of these events, which ones are actually likely to be black holes, now that we had some more confidence in our fit of this. And so these black points, these are the maximum a posteriors. This is kind of the peak of the distribution of those events. It doesn't show uncertainty at this point. And then we just said, okay, this region here, you had a 50% chance of being a black hole if you lied within there, based off of this PopSyCLE simulation. And so if you look at the number of events that fall within this region, there's 107 events, which were about 3% of the events, and 283 in the OGLE 4 survey, which were about 4%. So, that's a quick and dirty estimate. But in reality, if you look at this, getting back to these uncertainties, it's very hard to quantify the uncertainty of any given event. So here's the same zoom in of these regions, but with uncertainty bars, and you can see that they go all over the place. And so what a real analysis should do here is factor in that uncertainty. And so we wanted to take that into account. And so we approached this as a Bayesian type analysis problem, where we took these distributions from the simulations, we constructed probability density functions of each component, so the stars, the white dwarfs, the neutron stars, and the black holes. So now we can say, if some event lands in a particular location, what's the probability that it's consistent with belonging to that population? Now, of course, these separate components are not equally likely, because there's far more stars than there are black holes. And so that has to go into the relative weighting of these different components. What we then did was, given all of the MCMC estimates from each of these events, we evaluated the likelihood that that one of those MCMC realizations belonged to a given class, and then averaged over those to say, what's the probability that that particular event belongs to one of those classes? And so you can kind of see a map of this over on the right. So if one of your MCMC particles landed down here on the right, it was almost 100% chance of belonging to a black hole. Whereas if it were here in the middle, the shade, or the alpha on this, gives you the relative probability. The color tells you which class it's most likely to belong to. But you can see in here in this region, while it's still most likely to be a star, there's still less probability, because this kind of region overlapped with both the white dwarfs and the neutron stars. And then what we did, given all of those particles for any particular event, was we estimated the relative probability that that particular event belonged to, the star class, or the white dwarf, or the neutron star class, or the black hole class. And then whenever we looked at all 8,000 microlensing events, and we looked at the percentage, so again, any one of these events is likely to have some probability of being a star or a black hole. Given the uncertainty, it's still unlikely that one of these events is wholly, a black hole, but we can do this on by marginalizing over those events and their uncertainty, you can get relative fraction. And so these are the relative percentages here. But the interesting thing is whenever we compare this with the relative abundance from the simulation, we're finding, there were less stars, relatively speaking. But the interesting thing is that we find that there's about 4 times more black holes than the simulations or the theory would suggest. And interestingly too, there's also about 2 times more neutron stars. And so there's a few things that you can do to, why might we be seeing this excess of black holes and neutron stars? And so, obviously I think that there could be a systematic that we've not thought of or accounted for. There could be something incorrect with the Milky Way model that we used with PopSyCLE. Something could be incorrect with the stellar evolution model. Maybe we don't understand how objects go from stars to black holes and what their mass distribution should be. And then, if you want to consider a more radical alternative, this could be an additional component of the Milky Way that we hadn't modeled in that PopSyCLE simulation, which is considered stellar evolved black holes, that has some mass distribution that overlaps with both the neutron stars and the black holes. Now, if you ask me, there's an opposite axis to this, and that's probably likelihood of what the interpretation should be. And so I think, it's probably some systematic that we haven't accounted for. And so even though this is as direct a measurement as we could think of making, there's still tons of systematics in it. And so the next step that we're working on now is injecting primordial black holes into this. We're also exploring other, models of the galaxy. We're exploring different stellar evolution models. So we're trying to investigate some of those perhaps more likely systematics. And just in summary, I wanted to say that I think, these results are really exciting. As far as OGLE goes, we're kind of limited with that data, but it's really exciting future with things like the Vera Rubin Observatory and the LSST survey, or WFIRST, the Roman Space Telescope. And these are very complementary. And so you're going to get tens of millions of stars and billions of stars. You're going to get, about 100,000 microlensing events out of this, and much better characterization of the systematics. The other thing is LSST is going to probe everywhere. In the interest of time, I'm going to skip over some of this, but it'll produce fantastic observations of microlensing events and enable us, if it is a null measurement, enable us to really constrain the abundance of intermediate mass black holes. WFIRST is going to be fantastic as well. One other interesting thing that in the last minute I want to talk about is adaptive optics and things like the 30-meter telescope, GMT and ELT, as these are coming online. These are going to be very large telescopes, and so they're going to enable much better resolution than we've ever had. And so, if you look at this plot over on the right as a function of mass, anything below the black curve tells you whether or not the adaptive optics or the space-based resolution would be smaller than the Einstein radius here. And so what that means is that you could actually measure the multiple images. And this would provide definitive measurement of the mass of these objects, which is pretty fantastic. And so there's a large region of parameter space that with things like JWST, you could start to measure their mass. And then also the 30-meter class telescopes. And as an example of a simulation, this is what a 1,000 solar mass microlensing event observed with TMT would look like. And so what you can see here is you can see the multiple images of that star with time. And so I'll end here. I'll just say, I think, be careful with null bias. Hopefully I've convinced you that microlensing is a powerful tool. We've identified a powerful new means of finding black holes in the Milky Way. We're currently finding more black holes than theory predicts. Yeah, and there's a really promising future for microlensing black hole science. And so I'll open it for questions. Thank you.
All right. Thank you very much for coming. That was a very, very nice talk. Any questions? George, just had a question.
Yeah, I agree. Thank you very much for a great talk. Certainly learned a lot about microlensing and the exciting potential for WFIRST and LSST. Can I ask a technical question first and then a more general question? A technical question is, when you did your probability density functions for the different classes of objects, you did that took into account the relative numbers of those objects in the simulations, right?
That's correct. That did.
Okay. So that alone doesn't explain the sort of bias towards, or the apparent overabundance of massive objects in your sample.
That's right.
Okay,
so
that was too easy. Right.
You're right. This is a big effect too, because there's way more stars than there are black holes. If you didn't do that, you'd end up with a huge prediction for the number of black holes.
Right. Okay, just checking. Okay, well then, so if you had to take your numbers now and give us a dark matter fraction from primordial black holes, what would it be?
Yeah, so this was really interesting. This is, so there's a junior scientist at the lab. She converted to staff. What she was doing was she was taking this PopSyCLE simulation. She was assuming an NFW profile, and then she was populating the galaxy model in PopSyCLE with these primordial black holes. And where the work stands right now is she started off assuming everything was 40 solar mass black holes, and put those into the simulation, and then looked at how that changed the event rate. In particular, what happened to the distribution of objects down here, because these are more in the stellar, in this PopSyCLE simulation, it doesn't have black hole mergers. And so you kind of cap out at about, 10 to 15 solar masses of these black holes. And so what she found was that you added more objects down here to the lower right, which is what you would expect. But interestingly, even if she did 100% black holes, she only predicted twice as many black hole events, twice as many events. So even though there's far more primordial black holes, which seems counterintuitive, but one of the things that's happening is that this took into account survey selection effects. And these surveys were limited to like 8 years. And as you get to these more massive black holes, such as 40 solar mass black holes, the probability increases that their time scale of those microlensing events is going to exceed the duration of the survey. And so that's why, she was only finding, twice as many, but still, so what this would suggest, and I don't think that you should make this assertion, but if you did make the assertion that that this excess is primordial black holes, then what this would suggest is that you've got a mass function that must be going lower than 40 solar masses. It can't all be 40 solar masses, because otherwise you'd only expect twice as many black holes as the theory predicted. And so, if you want to be, even more optimistic from a PBH sense, you would say, perhaps this is why people are now finding things in the black hole mass gap, right? We're finding objects in between neutron star mass and black hole mass, where traditional, initial final mass relation stuff predicts that there shouldn't be objects. And so I'm a conservative scientist. I pursue radical science, but I try to do it conservatively. And so I'm not willing to make that, but it is interesting. Excellent questions.
I think Brian was next.
Well, I think you sort of answered it. I was going to point out, and it turns out you've thought of these things, but I was going to point out that, your probability of getting a black hole depends on your simulation, which did not include the primordial black holes. So So the fact that you have more excess black holes coming out of this doesn't necessarily mean that the accuracy of the black hole masses or exact numbers are correct. It just means that it's definitely deviating from the model, right? That's basically the takeaway.
Exactly.
Okay.
Yeah, and so I think that's where this comes back. And so we've tried, I think we've done a pretty good job of investigating, a lot of the systematics. Some systematics, which I call out specifically, are related to the Milky Way model. So in the prediction of the abundance of these events, we've assumed a single Milky Way model. And there are things such as, it's surprising how little we actually know about our own Milky Way galaxy. So there's things like the orientation of the bar in the galactic bulge. The amount of inclination of that actually affects these numbers. And so if I were a betting man, and you asked me to bet my house on it, I would say that it's probably the Milky Way model that is responsible. And also, there's other things like the model didn't include black hole mergers or binary black holes. And so that's another thing, which these are all things that Jessica's Lou's group, we've got some fantastic graduate students in investigating all this and now incorporating that into the simulation. And so we should have a better handle on that soon. But if I had to guess, I would say it's probably this, just because it would be too exciting for it to be primordial black holes.
Well, yeah, thank you. And this was a great talk. I want to quit what I'm doing and join your team. So,
hey, that's awesome. I was trying to recruit Simeon to the dark side earlier. Simeon is really, like, I'm serious. He motivated me considering this more seriously, because when George came to me, I initially said, why waste my time on this? It's been ruled out. And it was just, there's still a lot of interesting hints, which I think are worth investigating. Because even, there's a conservative aspect to the science. So this is enabling us to learn more about black holes, the Milky Way model, stellar evolution than we would otherwise. And so even if these aren't all dark matter, like even if black holes don't make up dark matter, we're still going to learn a lot about, the astrophysics and stellar evolution. Everything from, just stellar evolution to general relativity to complex other physics that are involved with neutron star stability, for example, I think.
You were pretty convincing in bringing me to the dark side. Fred, do you have a question?
Yeah, I think you partly answered it already, but my question was about the model that you're comparing to. When you say that there's an excess of a factor of 4 in the black holes or a factor of 2 in the neutron stars.
Right.
I mean, it seems like fundamentally, so this is a model of the Milky Way and stars in the Milky Way and stellar populations in the Milky Way. Is that correct?
Yeah, that's right. So it's both got the structure of the Milky Way as far as its kinematics, so both distribution and dynamics. It's got the various components and relative abundance of stars in each component. So you've got thick disks, thin disks component of the model. You have stellar age, which is an important factor because the assumed stellar age of the various populations goes into how many of these stars you think converted into black holes. You have the initial mass function, which is very important. And so I think the thing that's enlightening about this is even with something as direct of a measurement as microlensing is, you're still, hampered by so many complex systematics. And so this, I think, sorry, let me get to your question about.
Well, I mean, I guess it was more I guess I'm just expressing some general skepticism about how well you can constrain the upper end of the mass function for stars to predict the number of black holes, because we're talking about the very top of the mass function that would make a black hole in terms of these stars. And that's very poorly constrained, I believe. I mean, it's mostly an extrapolation from lower mass stars and some, I think you could play with that a lot. And a factor of 4 doesn't seem unreasonable.
No, no, and in fact, so Jessica, she's a far bigger expert in this than I am. She's often said that you're talking about essentially a factor of 10 flexibility there. And so I think you're going to be hard pressed with a factor of 4 to say whether or not it's something with the mass function or whether or not we're dealing with black holes. That is, we can start to get at this by looking outside of the bulge, for example, like looking towards the Magellanic Clouds, where there you don't have as many stars in between, and the relative fraction of dark matter to stars actually goes up. And so this is one of the reasons why LSST and these other surveys, which are going to probe the Magellanic Clouds as well, I think is powerful at breaking kind of this degeneracy between, are we just talking about something related to the astrophysics, or are we talking about something related to the dark matter halo?
Yeah, okay, thank you.
But yeah, you're spot on, I think, otherwise.
Any more questions? Okay, I did have one. So I'm guessing the answer to this is no for OGLE. If they were dark matter, their spatial distribution do you expect to be a bit different from the stars, right? You'd expect them to be more flat. And I was wondering if you could get something. I mean, you're pointed at the bulge, but maybe you could get some measurement in depth, but presumably not, because there's a mass degeneracy.
Yeah, actually, we had a paper. So I had a paper. Let me see if I can find it here. I skipped over it in the interest of time. Let's see, where did it go? But Michael Medford started to explore this, and so the first question is so you're absolutely right. You get very different spatial distributions between whether or not you're looking, in towards the bulge, and you're making certain assumptions about whether or not they're stellar evolved black holes, or they're primordial black holes that are making up essentially an NFW profile. And so one of the first questions we had was, would you even expect enough events in the outer galaxy? And so Michael Medford's work was showing that, yeah, even though the event rate is less because the density of stars is less, and so the probability of a black hole or some other lensing event passing in between that background star, goes down with that. Still with ZTF even, so current astronomical surveys, time domain, you'd expect over a number of years to have thousands of these events. And with that statistical power, you could start to tease out whether or not you're seeing the differences that you'd expect between PBHs or just stellar evolved events. So that's very important, and that's something that the current analysis, where I'm talking about this abundance, hasn't done that, because you don't get enough variety within the bulge itself.
Okay, any more questions? Okay, well, thank you again very much for what was a wonderful talk. And that's hopefully we'll be in touch soon. So
yeah,
thank you again for coming.
I want to thank you too, and thank you for all the engaging questions. As soon as things change, I really look forward to actually coming down to UC Riverside in person, and who knows, I might have a haircut by then too. We'll see.
Yeah. All right. Well, yes, we look forward to that. It'll be great to see you.
All right. Thank
again.
you.
So yeah. Bye bye now.
Bye.